Let's take a look at continuity. Now, in order for a function f of x to be continuous at the x value of a, three conditions must be met. So the first condition is that f of a is defined. So it's defined, the function is defined at the x value of a when I plug it into the function. Now the second condition is that the limit of f of x as x approaches a exists. So the limit exists from both the left hand side and the right hand side. And the third condition is that the limit of f of x as x approaches a is equal to f of a. Now the main formula or the main condition you want to focus on is the third one, where the limit of f of x as x approaches a is equal to f of a, because if this is true, then all three of these conditions are true and the function is continuous. Now keep in mind that if any of these conditions are not met, that's how we know the function is discontinuous. Now, if there are continuous functions, there are also discontinuous functions. So the first example of a discontinuity is a jump discontinuity. So it might look something like this. So notice you sort of have to jump in order to continue on with the function. Now the second one is a removable discontinuity, where you have the function and then all of a sudden there's a hole and then you can continue on with the function. So that's another type of discontinuity. Now the third type of discontinuity is an infinite discontinuity, and it could look something like this, where we have a vertical asymptote which sort of separates the function, making it discontinuous. So for this first set of problems, we have to explain why the function is discontinuous at the given number a. So for number 1, we have f of x equals ln absolute value of x minus 2, and the given a value is equal to 2. So once again, we're basically explaining why the function is discontinuous. So we have to go back to our three conditions that we mentioned earlier and try to prove why this function does not meet at least one of the conditions. So once again, the conditions are that f of a is defined. That's the first one. The second one is that the limit of f of x as x approaches a exists. And the third one is where the limit of f of x as x approaches a is equal to f of a. So let's go ahead, if I number these, let's go ahead and test out the first condition. So f of a is defined. Well, all we have to do is plug in our a value into the function. So we plug in 2 for a, or 2 for x in this case. So f of 2 is going to be equal to ln absolute value of 2 minus 2. 2 minus 2 is 0. So we get ln of 0. Now obviously ln of 0 is not defined. So we know that f of 2 is not defined. And because it's not defined, it does not meet one of the conditions. So we know that the function is discontinuous because it's not defined. So now for number 2, we have a linear function where f of x is equal to e to the x if x is less than 0, and then x squared if x is greater than or equal to 0, and our specific a value is 0. So let's go ahead and right away test out the first condition where f of a is defined. In this case, our specific a value is 0, so let's go ahead and test out f of 0. Now keep in mind, because we have a piecewise function, we have to choose our function based on the x value. In this case, we're plugging in 0 for x, and so we only choose e to the x if x is less than 0, and then we'll choose x squared if x is greater than or equal to 0. Since x is equal to 0, we're going to have to choose x squared. So we're going to plug in 0 for x here, and so we'll get 0 squared, which is equal to 0. So f of a is defined and is equal to 0. So now let's go ahead and test out the second condition, where the limit of f of x, limit of our piecewise function, as x approaches the a value, once again our a value is 0, so in this case x approaches 0, exists. Now once again, in order for the limit to exist, the limit from the left hand side must be equal to the limit from the right hand side. So I go ahead and write the limit of f of x as x approaches 0 from the negative direction must be equal to the limit of f of x as x approaches 0 from the positive direction, or from the right hand side. Now the same process here, we need to choose the function based on the x values. So on the left side of the equation, we're trying to approach 0 from the left hand side. So basically we need to choose the function that contains the x values that are less than 0. Since e to the x contains the values of x that are less than 0, on the left side of the equation we're basically trying to find the limit of e to the x as x approaches 0 from the negative direction. And on the right hand side, we're obviously going to pick x values that approach 0 from the positive direction, so the x values that are greater than 0, so we're going to have to pick x squared. So on the left side of the equation, it's going to be the limit of x squared as x approaches 0 from the positive direction. So now in order to evaluate the left side of the equation, I can just go ahead and use direct substitution and plug in 0 for x. So then we get e to the 0, which is equal to 1. Now on the right side of the equation, for this limit, I can also use direct substitution. I plug in 0 for x, and so we'll get 0 squared, which is equal to 0. So obviously 1 is not equal to 0. So that tells us the limit from the left-hand side is not equal to the limit from the right-hand side, which tells us that the actual limit of f of x as x approaches 0 does not exist. Because it fails to meet one of the conditions, we can say that it's discontinuous once again because the limit of f of x as x approaches 0 does not exist. So now for number 3, we have f of x equals another piecewise function. So we have x squared minus x minus 12 over x plus 3 if x is not equal to negative 3. And then we also have f of x equals negative 5 if x is equal to negative 3, and our a value is negative 3. So let's go ahead and start out with the first condition where f of a is defined. So let's go ahead and plug in negative 3 for x. So we're going to find f of negative 3. Once again, we're going to choose our function based on the x value. Since we are plugging in negative 3 for x, we have to pick negative 5. So f of negative 3 is equal to negative 5. And that's basically it. So because it's equal to negative 5, the function is defined. So we can go ahead and move on to the next condition. Now the next condition is obviously the limit of f of x as x approaches the a value. In this case, the a value is negative 3 exists. Now once again, for the limit to exist, the limit from the left-hand side and the right-hand side must be the same. So the limit of f of x as x approaches negative 3, once again from the left-hand side or from the negative direction, must be equal to the limit of f of x as x approaches negative 3 from the positive direction or from the right-hand side. So now once again, we're going to choose the function based on the x values. So for the left side of the equation, we have the limit of f of x as x approaches negative 3 from the negative direction. So we need to pick a value we need to pick a x value that's less than negative 3. Well, if we look at the piecewise function up here, f of x equals negative 5 is only defined at the specific x value of negative 3. And x squared minus x minus 12 over x plus 3 is defined everywhere else but negative 3. So the x value just cannot be negative 3, but it can be anything else. Now because we have to approach negative 3 from the left-hand side, or pick a value that's less than negative 3, we have to choose this function, because this function is defined everywhere, once again, except for the x value of negative 3. So we're basically trying to find the limit of x squared minus x minus 12 over x plus 3 as x approaches negative 3 from the negative direction. That's going to equal the right-hand side of the equation, the limit of f of x as x approaches negative 3 from the positive direction. Now in this case, we need to find, or we're choosing x values that are greater than negative 3. Once again, f of x equals negative 5 only exists at the x value of negative 3, at that specific x value. But we are looking for values that are greater than negative 3, so we have to pick this function here, since x can be defined everywhere except for negative 3. So we're going to find the limit of x squared minus x minus 12 once again over x plus 3, this time as x approaches negative 3 from the positive direction. Now let's go ahead and first evaluate the limit of the left side of the equation. So once again, I'm going to try direct substitution. I'm just going to plug in negative 3 for x. But when I plug in negative 3, notice in the denominator, negative 3 plus 3 is 0. We're going to end up dividing by 0, so that doesn't exist. So I need to find a way to simplify this entire fraction. Well, realize x squared minus x minus 12 can be factored. If I go ahead and rewrite it, get x squared minus x minus 12 over x plus 3. I'm thinking of two numbers that need to multiply to negative 12 and add to negative 1. Well, those are going to be x plus 3 and then x minus 4. So we've broken this down into x plus 3 times x minus 4 over our denominator, which is obviously x plus 3. Realize the x plus 3's will cancel, and so we're only left with x minus 4. So now I can go ahead and rewrite the limit with the new simplified function. So the limit of x minus 4 as x approaches negative 3 from the negative direction. And now I can use direct substitution, plug in negative 3 for x, so then we get negative 3 minus 4, which is equal to negative 7. So I'm just going to go ahead and write negative 7 underneath the left side of the equation. And so now we evaluate the right side of the equation. Realize it's the exact same fraction, and we've already simplified it down, so we can go ahead and rewrite it as the limit of x minus 4 as x approaches negative 3 from the positive direction, which obviously we can use direct substitution. Negative 3 minus 4 is also negative 7. So because negative 7 is equal to negative 7, or in other words, the limit from the left-hand side is equal to the limit from the right-hand side, we can go ahead and say that the actual limit of f of x as x approaches negative 3 exists and is equal to negative 7. So now we can go ahead and test out the third condition, where the limit of f of x as x approaches negative 3 is equal to f of negative 3. Well, however, in this case, the limit is negative 7. Negative 7 does not equal to f of negative 3, which is negative 5. So because it fails to meet the third condition, we have to say that the function is discontinuous, once again because the limit does not equal to f of negative 3. So now for these next set of problems, we have to state the domain of the function. So for number 1, we have f of x equals x over x squared plus 5x plus 6. Now in order to find the domain of the function, or in other words, in order to find the range of x values on which the function exists, it's easier to first find where the function does not exist, then we can go ahead and state the domain. So since we do have a fraction here, the only place where the function does not exist is where the denominator equals 0, because obviously we can't divide by 0. So how could we find where the denominator equals 0? Well, we can just set the denominator equal to 0. So I'm going to go ahead and set x squared, go ahead and rewrite that. We have x squared plus 5x plus 6. We're going to set that equal to 0. And so we can go ahead and factor x squared plus 5x plus 6 into x plus 2 times x plus 3. So then our x values are equal to negative 2 and negative 3. So at the x values of negative 2 and negative 3, they make the denominator equal to 0, which is where the function does not exist. So now, given where the function does not exist, we can go ahead and state the domain. So you can write this in interval notation, you can write this in set notation. I'll write it in both notations. So let's go ahead and first start with interval notation. So the function exists everywhere except for negative 2 and negative 3. So we can go ahead and write it as negative infinity to negative 3, and then union negative 3 to negative 2, union, and then finally negative 2 to infinity. So that's how you can write it in interval notation. Now in set notation, it's a lot faster. You just write it like so. So you just use this curly bracket here, and you write the function exists for the set of all x values, and that vertical line is going to be such that. So this function exists for the set of all x values such that x cannot be equal to negative 2 and negative 3. And that's how you write it in set notation. So now for number 2, we have f of x equals x squared plus the square root of 2x minus 1. Now the only place where I can think of where the function does not exist is where we have a negative value inside of the square root, because obviously negative square root is an imaginary number. Now there are many different ways to go about this, but since we cannot have a negative once again inside the radical, I'm going to go ahead and set 2x minus 1 to be greater than or equal to 0. So if I go ahead and solve, we add 1 to the other side, so 2x is greater than or equal to positive 1, and then x is greater than or equal to 1/2. So basically we have that the function exists for all x values that are greater than or equal to 1/2. So we can write this in interval notation as from 1/2 to infinity. This is the easiest way to write it. And then in set notation, you use the curly braces once again for all x values such that the x values are greater than or equal to 1/2. That's how you write it in set notation. Now for number 3, we have f of x equals e to the x times sine of 5x. Now sometimes it can be tricky to find the domain of functions like these. So what I'm going to do is actually split this into two different functions here. So one of the functions is e to the x and the other one multiplied by sine of 5x. So if I go ahead and look at the graph of e to the x, the domain of e to the x is obviously just from negative infinity to infinity, so all real numbers. And then for the graph of sine of 5x, just think about the graph of sine of x. Instead, the graph is just stretched out 5 times more, because it's not just sine of x, but sine of 5 times x. And the domain of sine of 5x is also going to be from negative infinity to infinity, or all real numbers. Now, when you have two functions that both have domains of all real numbers, and you multiply them together, then the domain will still remain as all real numbers. So I'm just going to go ahead and write it in interval notation as from negative infinity to infinity.